I know differential equations. Sounds impressive, doesn't it? Well, it's not as impressive as it sounds. This is Climb Time, and in this video, we're going to learn related rates. And related rates are a form of differential equations, and we're going to see what that's all about. Okay, so let's say we have a little situation here. We have a wall and we have a floor, and this green thing right here is a ladder. So this ladder is going to have length L. So we're going to say this is length L. And again, I'll just label this real quick. This is the floor, the ground, and then this is a wall. Okay, and so the idea is that this ladder is a fixed length, and this ladder is going to be a certain height up on the wall and a certain distance from the floor. And the idea behind related rates is if this ladder if it were to start to slip and start to fall down, there's some things that would change and there's some things that wouldn't change. What wouldn't change is the length of the ladder. The ladder is assuming it's a fixed ladder and it's locked in place in terms of its length. So what wouldn't change is the length of the ladder. If it's like a wood ladder that doesn't extend or anything, the length of the ladder would not change. So as it went to fall, L would always be length L. However, what would change would be its position from the wall. So I'm going to call that X. Okay, so that would be the distance away from the wall. And what would also change is the distance up on the wall where the top of the ladder meets. We'll call that Y. Okay, so we have Y and we have X, and we give them variable names. L looks like a variable, but it's not really a variable. It's a constant. It's not going to change as this ladder slips and falls to the ground. So L remains fixed. Y will get smaller over time if the ladder's falling to the ground, and X will get bigger over time as it falls to the ground. So the question is the rate at which X changes and the rate at which Y changes, how are they related to one another? And that's why this is called related rates. We're trying to figure out how those rates relate to one another. Are they the same? Is the change in X equal to the change in Y if we have a ladder of fixed length L? Do they depend on the distance from the ground? Do they depend on X? Does the rate of these two depend on X or Y? Well, we're going to find that out. And so that's the process we're going to go through doing something called related rates. All right, so let's start with the steps. Here are the steps. The first step is to find an equation between the variables. So we see that we have a variable X and a variable Y, and there's going to be a rate at which X changes, there's going to be a rate at which Y changes, and then the rate at which L changes is 0 because it is not changing. So we want to find a variable between X and Y and L. And so what you might recognize there is we have a right triangle. And so if we have a right triangle, we can do the Pythagorean theorem. So the Pythagorean theorem is going to look something like this. We're going to have x squared plus y squared equals L squared. So step one is to find an equation that relates the variables together. So whenever we're working with a related rate problem, we're probably going to be given a rate, and they're going to ask you to find a rate. But they won't always give you the equation that relates the variables together. So you've got to find the equation yourself a lot of times. So in this case, we'd use the Pythagorean theorem to find how these variables relate to one another. And of course, L is constant. L does not change. X and Y will change in this problem. As the ladder slips and falls to the ground, X and Y will change, but L will not. So that's step one, is to find an equation between the variables. Step two is to perform implicit differentiation. And implicit differentiation is something that we assume you know at this point. I have another variable on that if you want to, another video on that if you want to check it out. But this is how I do implicit differentiation. I start by taking the derivative of the first term, 2x, and whatever my variable is, I put the differential afterwards. So I say dx, not y, x. So 2x dx. And then I move on to the next term. And the next term, my variable is y. So I take the derivative, which is 2y, and I put the differential afterwards, which is dy. And then the last term is L squared, and L is a constant, it does not change. So since it does not change, the derivative of L squared would be 0. However, I could say 2L dL, and then recognize that dL is 0 because dL represents the change in L. And since L does not change, dL would be 0, and that would also make it 0. So I could take another step if I want to and say 2L dL, and then plug in 0 for dl afterwards, or I can just say 0 now because I know L does not change in this problem. L will slip and fall to the ground, but L will always be length L, whatever it is. So that is step 2, do implicit differentiation. What I'm looking for is rates. I want to know how much something changes with respect to time. So another thing I have to do in step 2 is divide all my terms by dt. So if I divide all my terms by dt, I say over dt, I say over dt, I take 0 over dt. And by the way, if I had dl over dt, that's fine because dl over dt is 0. It does not change with respect to time. So it still works, even if I said 2l dl. I would divide by dt everywhere, and I plug in 0 for dl over dt. All right, so I have 2 rates here. I have the rate at which x is changing. I have the rate at which y is changing. And so step 2 is implicit differentiation. I've done that. And now I have 2 rates. And by having an equation, I can already see that they have a relationship. The equation is the relationship. This is the relationship between 2 rates. And it's also what we call a differential equation because it's an equation with differentials in it. dx is a differential, dy is a differential, dt is a differential. So it's an equation with differentials in it, and that makes it a differential equation. It's also a relationship between 2 rates, so it would be a related rate problem. So step 2 is do implicit differentiation. Step 3 is to solve for the rate we want. So let's assume we are looking for dx over dt. We want to know what's the rate at which x is changing, and so that's the thing we're looking for. So I want to solve for dx over dt. So if I solve for dx over dt, my first step would be, honestly, this is what I would do. I would see these both have a 2 in common and a 0 over here. So I would divide all 3 terms, this term, that term, I'd divide it by 2. So by dividing by 2, basically the 2's go away. My next step would be to move the y and the dy over dt to the other side. So I'd have x times dx over dt on the left. And on the right, I would have negative y times dy over dt. All right, so that'd be my first step, is to move everything that doesn't have a dx over dt in it to the other side. If I had multiple terms with dx over dt in it, I would want to get them to the same side first, and then I would want to factor out the dx over dt. So if you have multiple terms with dx over dt, and that's the thing you're solving for, get them together on the same side and then factor them out. Once you factor the dx over dt out, you're going to have something times dx over dt on this side. On the other side, you're going to have all the terms that don't have dx over dt. So on one side, it's dx over dt. On the other side, it's not dx over dt. And now we divide by x on both sides. And if I do that, we'll just go ahead and show it like this. I divide both sides by x, and so I get dx over dt equals negative y over x times dy over dt. I guess I'll write again just to make it look nice. So dx over dt, which is the thing I'm looking for, is equal to negative y over x times dy over dt. All right, so that is me solving for the rate I want. I want to know how quickly x is changing. Okay, so let's talk about our example real quick and see what this means. Our example is that the ladder is slipping and falling to the ground. Since the ladder is slipping and falling to the ground, that means x is getting bigger with respect to time. So I would expect x is changing and it's getting bigger. So since x is getting bigger as it's changing, what we know is that dx over dt, and I'll write this over here, dx over dt must be bigger than 0. I know this because x is getting bigger with respect to time. If x is getting bigger, if this distance is growing as the ladder slips, then that means dx over dt must be positive. In the same token, I know that y is getting smaller. I know that as this is slipping, y is getting smaller. As this falls down, the y value will get less and less and less until eventually y will be 0. And x will be L at some point because eventually the ladder falls to the ground. And so the distance because we're looking at the bottom ladder. So the distance from here to the bottom ladder will be L. So at some point, x will be L. In the beginning, x is whatever the starting point was. But x is going to continue to grow over time. And that's why dx over dt is going to be greater than 0 because x is getting bigger. Y, on the other hand, is getting smaller with respect to time. So I'm going to write that in. dy over dt must be getting smaller because it's slipping, it's falling to the ground. So therefore, it is less than 0. So dy over dt is getting smaller with respect to time, and dx over dt is getting bigger with respect to time. So that is the constraint of this problem. It's just how ladders work when they fall. It's a constraint of physics and physical objects. Now let's take a look at our relationship here. This is a related rate. This is the differential equation, and this is us solving for dx over dt. We can see that there's a negative sign here. So therefore, if dx over dt is positive, then dy over dt must be negative, or vice versa. If dy over dt is negative, a negative times a negative would make it positive, so dx over dt would then be positive. But the relationship between dx over dt and dy over dt is that they're negatives of each other. And we know this because y and x cannot be negative. Based on how I defined y and x will always be positive because x is going to be growing. It's not defined to be negative in any way. So x will always be positive and y will always be positive. So I might write that in as well so we don't forget that. So x is always positive and y is always positive. Okay, because x and y are always positive, that's why this equation describes what we expect to see, that dx over dt will be the negative of dy over dt. So dy over dt will always be negative if it's falling to the ground. Dy over dt will always be negative. A negative times a negative will make a positive, and dx over dt will always be positive. Now, that was assuming it was slipping to the ground. However, there's another option here, and this equation still holds. And the other option is that I'm pushing the ladder up. Maybe there's like a little wheel at the bottom here, or even there isn't a wheel, I can still push on it. And I'm pushing on the ladder and I'm allowing it to slide up to where eventually it's flat up against the wall. In that case, this is still true. These are no longer true, but this is still true. And what happens in that case is dx of dt would be negative because x is getting smaller with respect to time, and dy over dt would be positive because y is getting bigger with respect to time. But what is true in both cases, whether the ladder is slipping to the ground or the ladder is being pushed up against the wall, in both cases, dx over dt will be the negative of dy over dt. So that's why there's that negative sign there, and it comes out of the process of finding the differential equation. So what this tells us that dx over dt depends on the y position and the x position and the rate at which y is changing. So dx over dt depends on a lot of things. And so usually in these problems, they give you a lot of values because you got to plug in a lot of things to find dx over dt. One thing I want to point out here, though, is they don't have to give you x and y. They could give you x or y as long as you know the length of the ladder L. Because if you know the length of the ladder L, you can find the one you're missing. So if they give you x, you can find y if you know L. But they do need to give you dy over dt if you're going to find dx over dt. So let's just look at an example of what they might give you. So let's just say, for example, that they give you dy over dt, say it is falling, and they tell you that it's falling at -1 foot per second. Okay, so this is a rate. Y is changing at -1 foot per second. And let's say they also tell you the length of the ladder is 13. And say they also tell you that they want you to find dx over dt when y is equal to 12 feet. Okay, and this would be feet as well, 13 feet. All right, so how do we find dx over dt? Well, step 4 is just plug in what we know. So if we're just plugging in what we know, so we're looking for dx of dt. And so we just plug in what we know, and what we know is we know y, so we can plug in -12. We don't know x, but we do know dy over dt, it's going to be -1. So all I got to do is find x, and I can solve this. So in order to find x, I have to go back up to this equation here. I have to plug in 13 for L, 12 for y, and keep in mind that it doesn't matter if it's negative or positive because they're squared, but y and x will always be positive in this example. And solve for x. And so what you have here is what's called a 5, 12, 13 triangle. So if you do plug that in, you would get 5 for x. So I'll just show you real quick. So if you have x squared plus 12 squared is equal to 13 squared, get 169 minus 144. X squared is going to be the difference between 169 and 144, which is 25. And so x is going to equal plus or minus 5, but in this case, x is only positive, so it's 5. So -1 times -12 fifths is going to be 12 fifths, but what I want to point out to you is that the units do matter. A lot of times you have to put units in. So your units are going to be, it's a rate of change. It's how quickly x is changing with respect to time. And we are talking about feet per second. Y is in feet per second, and so is x. And that is how quickly x is changing. It's getting bigger at 12 fifths feet per second. But what I want to point out is that the rate of change of x depends on both the rate of change of y, which could itself be changing because gravity accelerates things. So it's very likely that y's rate of change isn't constant in this whole process either. But the rate of change of x depends on the rate of change of y, but it also depends on where the positional ladder, where it's at in terms of x and y. So while they might only give you the y position, you do need both the y and the x position. So they need to give you at least one more piece of information so you can find the x position. So that is the process you go through for a related rate problem. It is a type of differential equation. So this is the original equation, and this is a differential equation. It's a type of differential equation. And so you go through these steps, find the equation between the variables, implicitly differentiate, solve for the rate we know, and then plug in what we know. I'm sorry, solve for the rate we want is what I meant to say. Solve for the rate we want and plug in what we know. Now, sometimes you can skip the order of steps 3 and 4. A lot of times you can plug in what we know first and then solve for what we want. And when people are first learning algebra, that they usually do 4 before 3, they plug in first and then they solve for what they want. But generally, it's a good skill to be able to solve for the thing you're interested in with just variables on the other side, because it's nice to actually be able to see the equation and see what it depends on before you plug in any values. It's also easier to do more types of problems because then you can just plug in the values for any situation, for any spot where L is at as it's falling to the ground.